Okay, welcome back. We've spent the last couple of sessions talking about essentially voltage and current. So what we're going to do today, or in this session, is we're going to introduce the third part of the equation when it comes to circuits, and that is resistance. Okay, resistance is another part of the equation when it comes to dealing with electric circuits and analyzing electric circuits. And we're going to sort of continue on with the same analogy that we used before. And you may remember, if you watched the last session, that we compared electric current to water flowing through a pipe. In other words, the water current through a pipe or a hose is very similar to the electric current or the electrons flowing through a conductor. Well, we can use the same analogy for resistance. But like I said, just to recap, current, electric current, we can compare that to the amount of water that flows past a given point in 1 second. Although remember, this is charge instead of water. Voltage is the force that pushes the water along. So if we think about the water analogy, then essentially what happens is the water supply is usually above where your house is. So gravity is what's providing that push. Okay, so electric potential energy or voltage is basically work being done on the charge to give it some potential energy. And resistance then is anything that resists that flow. Okay, think of things like friction, right? Friction resists motion. So in our water pipe, for example, there could be areas where there's a lot of stuff built up on the inside of the pipe. There might be rust there. There might be small pebbles. There might be places where the pipe has been crushed a little bit, so it's a bit narrower. So that restricts the flow of water. So for electric current, it will be the same thing in a wire. There's certain things about the wire that could restrict the flow of current and therefore offer resistance. Okay, so let's talk a little more about resistance then. Okay, Ohm's Law is a good way of relating voltage and current in a circuit. So let's just take a look. If we had a simple circuit like you see here, and you've seen this diagram before if you've been following through the slides I've been showing you. We got a battery, we got a light bulb. Doesn't get any simpler than that. We've got a voltmeter to measure the voltage across the light bulb, and we've got a current, or an ammeter, sorry, to measure the current in the circuit. And when we connect it, we can get readings. And if we add more batteries, or if we were using a variable power supply, we would actually see a relationship between voltage and current. What you'd find is the ratio of voltage over current would remain fairly constant in that circuit. As we up the voltage, the current would go up as well. And the relationship is one that we call Ohm's Law. And called Ohm's Law because a guy by the name of George Ohm is the one who discovered that relationship. And the relationship is simply this: V equals I times R. The voltage in a circuit is the current times the resistance. And we can rearrange that in terms of I or R, right? We could say I equals V over R, or R equals V over I. Okay, it can be arranged anyway. That equation, Ohm's Law, V equals IR, that is on your data sheet. Most of you probably already have it memorized anyway, but it is there just in case. So that's the relationship. Okay, Ohm's Law can be stated as follows in words. We could say the current in the circuit is directly proportional to the voltage as long as the resistance doesn't change. And for the most part, that's true. The resistance usually doesn't change. Now there are factors that can make the resistance change, but for the most part it doesn't. So if V equals I over R, then we can rearrange that as R equals V over I, R for resistance. And resistance then is going to be volts divided by amps, V over A. But we give that a new name. We call that an ohm, again in honor of the guy who discovered the relationship in the first place, George Ohm. He was a German. Anyway, The symbol for ohm is the Greek letter omega. Okay, and 1 ohm is 1 volt over 1 amp, a volt per amp. Okay, and remember that relationship because that may show up as a multiple choice question sometime as well. So always nice to know it. So let's look at how these things are related. Well, a resistor that follows Ohm's law, in other words, a resistor where that ratio of voltage to current is always equal, that is what we call an ohmic resistor. An ohmic resistor. In other words, follows Ohm's law. In other words, the voltage versus current graph would always be a straight line. Okay, so you can see this one here, for example. These are 3 different resistors, or it could be the same resistor changed in some way. But you notice the line stays straight. See that? That straight line tells us that the V over I is constant. In other words, constant slope. Okay, now all materials don't act like that. In fact, most materials, if we put enough current through it, is not going to behave like that indefinitely. Eventually, something's got to give. Okay, the material will start to get too hot, it'll start to melt, and something will change. But a lot of materials are ohmic for a while, and then all of a sudden, once they get to a certain voltage, a certain current, they become non-ohmic. In other words, Ohm's law is not followed anymore. This is what most materials are like. They're ohmic up to a point, and then something changes. Usually because the material gets hot, and temperature does affect resistance. Okay, so when the material gets hot, the resistance does change, and then Ohm's law kind of gets thrown off a bit. But at lower voltages and currents, a lot of standard materials do act as an ohmic resistor. Sometimes, though, they don't. Like these things, right? These things here are what we call a completely non-ohmic resistor. In other words, doesn't follow Ohm's law. The ratio between voltage and current is not a constant. There's no constant slope. This one, for example, if you took an LED, a light-emitting diode, and you've seen lots of examples of those. Okay, you probably have one in your cell phone, right? It glows usually red while your cell phone is charging. Then once it's charged up, sometimes it turns to a different color, like green. Okay, or your TV's probably got an LED on it. But what happens is, LEDs would follow this relationship. Starts out like this. As the current goes up, voltage goes up, okay, and it reaches a point eventually, and we call this the knee voltage at this point, where all of a sudden the current shoots up very quickly. And in most devices, that's an indication that it's time to stop charging. Now let's turn the LED to a different color, because we got this high current coming through now. That means that we've reached the maximum voltage in this battery that we're charging, and it's time to turn the charging circuitry off. So these types of circuits have their uses, for sure. But in most electric circuits, we're looking for the ohmic, okay, the ohmic relationship. But this is the relationship right here. If you get a nice straight line, that's an ohmic resistor. If it's a curved line, it's a non-ohmic resistor. It doesn't follow Ohm's law. Okay, like I said, that could show up in a question somewhere along the way. So remember that. Remember that. So let's look at the factors then that affect resistance, because there are things that affect the resistance of a material. The most obvious one is the length. Okay, the longer the wire, the more resistance it has, obviously. Okay, and that makes sense when you think about it. Just like a longer pipe has more resistance to water flowing through it. Well, a longer conductor has more resistance to electrons flowing through it. In fact, it's a nice proportional relationship. If we double the length, we double the resistance. If we half the length, we half the resistance. Okay, so that's a nice, even, standard proportion there. That's one factor. The second factor, cross-sectional area. In other words, if we took, like a circular wire, is fairly straightforward. We take a circular wire, we take a slice off of it, you look at that slice, it's a circle. And the area of that circle, the area of that cross-section, is also, there's a relationship between resistance and that area. But as you can imagine, as the wire gets bigger around, more electricity can fit through it. So the bigger around it is, just like a bigger pipe, it's going to have less resistance to the flow. Okay, less resistance. And that makes sense too, right? With water, a bigger pipe can carry more water. For electricity, a bigger wire can carry more current too. Same idea. This time, though, it's an inverse relationship, that means, right? So, in other words, if the area is doubled, the resistance is halved. It's it's inversely proportional. It's in what we call an inverse proportion. No squared there, at least not in terms of area. There's no squared. So it's inversely proportional. One goes up, the other goes down by the same proportion. So we call it an inverse proportion. Okay, so those are the two proportional. Those are the two proportionality relationships. Then we've got type of material. Also important. Okay, some materials obviously are better conductors than others. Like copper wire is a pretty good conductor. Aluminum is a really good conductor. Gold is even better, but obviously we don't make wires out of gold because they'd be too expensive. But often in high-end stereo equipment, the connectors are gold-plated for that reason, because much better resistor. So the type of material affects the resistance. And a general measurement of that is something called resistivity. The resistivity. And the resistivity depends on the material itself. It's a constant. So for copper of a certain purity at a certain temperature will always have the same resistivity. Always have the same resistivity. And the fourth thing that affects it is temperature. And this table, by the way, is straight out of your textbook as well. And we're going to look at some of these relationships now in a bit. Anyway, the temperature also affects resistance. Okay, generally, the way it works is this. As the temperature goes up, generally the resistance goes up as well. Now, there's not a proportional relationship this time, so there's no way to really factor that into our equation. Okay, it's not a proportional relationship. Okay, but what happens is, as the material heats up, the molecules that are in that wire start to vibrate faster. They're moving around. And that makes it harder for the electrons to push their way through, because there's not as much space now in the middle anymore. Okay, these electrons are squeezing through the empty space basically between atoms. And if the atoms are jumping around a lot, then they're impeding the flow of the electrons. So higher temperature does give you higher resistance, although it's not a proportional relationship. So there's no equation that we can factor in. But there is an equation for the rest, as we will see. Here's the equation. Remember, we said resistance was proportional to length, okay? And we also said resistance was inversely proportional to area, so I say 1 over area. Put the two of those together, resistance is proportional to length over area. Now, we can make that an equation by putting in a proportionality constant, and the proportionality constant is this guy right here. That is the Greek letter rho. Rho. And the Greek letter rho stands for resistivity, which we said a few minutes ago, or just a minute ago, that resistivity is a measurement of the general resistance of a material. And again, it depends on the type of material we're talking about. Good conductors have a very low resistivity, whereas poor conductors have a high resistivity. And that factors into the equation. This equation right here, that's on your formula sheet. That's how we can find the resistance of a material if we know the length and the area and the resistivity. Now, sometimes instead of the area, you might be given the radius. So all you got to remember then is the formula for the area of a circle, because we're always talking about circular conductors, would be pi r squared. And we're going to do an example like that. Okay, so that's the general resistance of a material. Now, when we start talking about resistance in circuits, you have to remember there are two different types of circuits. There are series circuits and there are parallel circuits. Series and parallel. So in a series circuit, it means that all the elements are connected together in a row. In other words, there's only one path for the electrons. And if that's the case, the resistance, the total resistance, is calculated in a certain way. Okay, the total resistance is calculated in a certain way. If it's not connected like that, if it's connected in parallel instead, then we calculate the resistance in a different way. In a different way. So let's look at those two cases. Let's look at those. Series first. Series circuit. When there's only one path, in other words, when the electrons have to go through each of the resistors in turn, then the resistors add up. It's simple. All you got to do is add them together. So for this example right here, we've got resistor 1 is 10, resistor 2 is 20, resistor 3 is 30. There's a single path around that circuit. Every single electron that leaves the battery has to go through all of those resistors in order to get back to the battery. So the total resistance is the sum of those. So 10 plus 20 plus 30. 60 ohms of resistance. Now, there's a couple of general comments you can make there. In series, first of all, the total resistance is obviously larger than the individual resistances because we're adding things up. We're taking the sum. So that means that adding an extra resistor in series will always give you a larger total resistance. It always increases the total resistance. Now, that seems to be common sense, and it is. But in a parallel circuit, that's not the case, as you'll see in just a second. So let's take a look at the parallel circuit. In a parallel circuit, there are several parallel paths. In other words, an electron that leaves this battery and starts to travel around the circuit like this, when it gets to here, there are choices. It could go this way and go through resistor 1 and then back to the battery, or it could go through here, resistor 2, and back to the battery, or it could go this way and back to the battery. Kind of like a car going from point A to point B may have a choice of different routes it can take. Well, the electrons here have that same choice. So that means that kind of like, I mean, if you have one highway, only one route, all the cars had to go that route, it's going to take longer because the cars are going to be moving slower. But if there's 3 different routes you can use, that's probably going to speed things up when you think about it, right? Because that means a lot more cars now can get from A to B because they got 3 different ways to go. So you can handle probably 3 times as many cars, right? So that's going to reduce the total resistance. So here's the way you find it when they're in parallel. 1 over R total, when it's parallel, is 1 over R1 plus 1 over R2 plus 1 over R3. So the same 3 resistors, 10, 20, 30. I'd have to say 1 over RT equals 1 over 10 plus 1 over 20 plus 1 over 30. And then we could find the lowest common denominator, which is one way to solve this. I could say the lowest common denominator for these 3 values would be 60. So I got 6 over 60, that's the same as 1 over 10. 3 over 60, same as 1 over 20. 2 over 60, the same as 1 over 30. Add them together, you get 11 over 60, but remember that's 1 over the total. So the total would be the reciprocal, which is 60 over 11, or 5.5. Now, trying to do it that way by finding a lowest common denominator is not always easy to do. It was pretty easy with those numbers because they were nice round numbers that had a fairly easy common denominator. That's not always possible. Sometimes, for example, the resistances are going to be decimal numbers. That makes it extremely hard to find common denominators. So it's a lot easier to use the reciprocal button on your calculator. And the reciprocal button on your calculator could look 2 different ways. It could be 1 over x, or it could be x to the negative 1. It depends on which calculator you have. Okay, and it might be in a different place on your calculator. Sometimes you might have to use the second function or the shift key to get at it. But that's the key you're looking for. X to the negative 1 or 1 over x, one or the other. So then in order to do that, I would say 10 x to the negative 1 plus 20 x to the negative 1 plus 30 x to the negative 1. You do all that in one step, and it equals this. Then you go your answer, x to the negative 1, and you still get the same number, 5.5. Okay, and it's much easier to do it that way using your calculator than it is to try to find the lowest common denominator. Okay, so you really need to know how to use that button on your calculator. Now, again, some notes. When resistors are connected in parallel, it turns out that the total resistance is actually smaller than any of the individual resistors, right? These here, we had a 10 and a 20 and a 30 put together in parallel, and the total resistance is only 5.5. That was less than any of the individual resistors by themselves. Now that's kind of counterintuitive, isn't it? Okay, that kind of doesn't really make a whole lot of sense. But think about it this way. It's kind of like a 3-lane highway. Each lane of that highway has the same resistance as a single lane did, but because there's 3 of them, you can handle more traffic. So that decreases the total resistance of that highway because you've got 3 paths now instead of 1. Okay, that's the reason that happens. So when you're finding parallel resistance, it's always lower than the individual resistors are. So that means that every time you add an extra resistor in parallel, you get a smaller total resistance every single time. It gets smaller every time. Okay? Always getting smaller, decreasing, decreasing, decreasing. So before I get into any questions, any sample questions from old publics, I'm going to pause here now because we're up over 20 minutes, and I try to keep these things down around 20, 25 minutes wherever possible. So we're going to start another recording before we look at the sample questions. So we're going to pause right here. So there's going to be a part A and a part B this time, and part B is going to be the questions that we're going to look at. We're going to look at sample calculations involving resistance and Ohm's Law. So we'll get those started in a little bit. So again, good luck with your exam, study hard, and please come back and watch some more of these sessions. So part B will be a separate recording.